anyone else? Is everything is okay?
Yes.
Okay. Okay, so before I go to the ANSYS side, first I will start with this slide that is based on the laminar pipe flow at the Reynolds number is equal to 100. So basically, when you talk about the any flow, that flow is like is characterized by the its Reynolds number. Reynolds number will determine its nature, like the flow is turbulent, laminar, transitional, or how it will behave. So anywhere you will be seeing any fluid dynamics study, including the CFD part also, that they will always mention the Reynolds number. Reynolds number is the most important a formula or the thing in the fluid dynamics. So that's why we always start with the Reynolds number. And from Reynolds number, many people now, I don't know at the moment what people are thinking right now, but like in the few years back, people used to think that is there any way to input the Reynolds number to the CFD software? So answer is that no, we cannot input a Reynolds number to CFD software directly, but through its formula, that is the density times velocity times length. Or this dimension is basically is the characteristic length of the flow. So this characteristic length can be the diameter in the pipe. This can be the length, for example, chord length. This can be the for example for combustion chamber. This can be the like a diameter of the primary holes, secondary holes, tertiary holes. So depending on that, the which dimension is going to affect the flow most, the dimension will be used over here. Okay, and divided by this is going to be viscosity. So these I will discuss these things in detail. So we have to actually input these four parameters into our CFD simulation. The density and the viscosity, they are fluid properties. Velocity is a flow property, and the diameter is the geometrical parameter that you will get from the geometry modeling. So these four inputs are required when we decide about any CFD simulation. Okay, and then we are going to validate with the analytical solution. But I will be driving the analytical formulas first, and then we will move to our CFD side. Okay, this is the whole idea about this workshop. So I'm calling this one as a course because this contains very detailed about everything here. Very simple problem, but it contains like a lot of details here. So we are going to be driving the analytical formula for velocity profile, pressure drop, wall shear stress, maximum velocity, fraction factor, coefficient of fraction, or the Fano fraction coefficient. And the same thing we are going to extract from the CFD simulation. And then we get the different parameters such as velocity, density. So this is like, okay, so any problem whenever this is a very important aspect. Whenever you are going to solve any CFD problem, the first thing is that you must know what is going to be the input. Okay. And then what is going to be the output? No, you are not going to know the exactly output values. Otherwise, there's no point of carrying out the CFD simulation. But you should be having the idea that the results would be like this one. So based on your theoretical knowledge. So when you get the CFD solution and you are going to extract the graphs like contour plots, vector plots, XY plots, so you can know that the solution is correct or may not be correct. So only for up to that idea that you can judge the solution, that solution is correct or not. Not exactly knowing the answer, but you should have the idea. And then definitely we have the black box that we must know what is going inside. So like this is like this scheme, okay? But problem is that people at the moment they don't know about what is going to be the over here. This is like a CFD solver, Fluent CFX. So we must know that what we are going to choose. For example, let's say our problem is laminar. So how the flow is laminar and why it's a laminar, or why the flow is turbulent. If the flow is turbulent, then what aspects are important for the turbulence? For example, for the high Mach number flows, the boundary layer is not important. Boundary layer is very, very thin. So in that case, the shock wave is important. Okay, so shock wave is important, and at the hypersonic flows, The heat transfer rates are very important on the body of the, for example, re-entry vehicle. So this should be known to you that what aspects are important for your case. So you have to turn on that particular model in CFD software. And for example, you are running the turbo machinery simulation like wind turbine. So you must know that the steady state solution would be enough or transient simulation should be there. Some problems, they don't have a steady state solution. So they always go for transient simulation. So you must know that when you are going to be running transient simulation, when you're going to run the steady state. And then from transient simulation, there are the two possible solutions. Either you are going to be concentrating on the end solution, that what is going to be the end result after this much time, or maybe you're interested in the like developing solution. Like for example, when the sun is rising on in front of your building, so you want to see that how this sun is going to heat up your building from inside. So, and based on that heating, you can decide about your air conditioning loads in the very big plazas. So you must know that the which solution method is is going to be working here. For example, again, combustion process. So which combustion model you are going to apply and why. So these things, you must know, and this is what I'm trying to do actually in this course, that what aspect you should be selecting and why, and what should be your input and what should be your output, expected output, and what should be input to your CFD software. So inputs can be the like a boundary conditions, your mesh, your geometry, and your selection of these parameters. Okay. So now any CFD process will start with the geometry. So either you make the geometry in some CAD software, for example, SolidWorks. And actually, I would recommend that the geometry is complicated, then go for SolidWorks. Even for simple geometries, we can make them in Design Modeler or Spaceclaim. That is the ANSYS geometry modeling tools. But I would suggest that you should, if you if you don't have the idea about the CAD modeling, you didn't learn about CAD modeling, then as an engineer, I urge you that you should be learning about these softwares. They are very important in the engineering. Okay. So, but as the geometry gets little complicated, you have to go to the some CAD software, SolidWorks, CATIA, or Parametric like these. So, question is that then what is the purpose of Design Modeler or the Spaceclaim? Their important their use is that they are basically used for correcting geometry. Like when you import geometrical model like CAD models, they have some errors, not errors in the geometry, but from CFD point of view, they are not connected different surfaces of the gaps. They are the overlapping surfaces. There are maybe the different extra edges there. Maybe our geometry is, for example, this is a very simple geometry. So this geometry might have the like you can see the hole here, gap here. So you have to fill this gap. So these things are done in the CFD in these geometrical tools in the ANSYS. So for example, one more thing, then you have when you import geometry. So CAD modeling person might have made the geometry like in this way. Sometimes they do. They start from there. Sometimes what they do is that they have done the geometry here. So today they have done the part up to here. Second part, they may start from the here in this way. So this is okay for manufacturing purpose for CNC machine, but from CFD point of view, they are two different surfaces. They're not connected and they are overlapping some regions. And this will make the issue for the meshing, because meshing is going to be continuous. Okay, it cannot have the breaks or overlapping cells, so it should be continuous. And only one single cell should be on the one location. So these softwares are basically, they have the capability to repair these problems. Or sometimes we have to modify them. And the last and the most important aspect of any of these geometry tools are basically is to make domains. Internal domain or the outer domain. For external flow or for internal flow. For these tools are used actually for this purpose. But definitely we can make the pipes, we can make the simple aerofoils, we can make the simple blades in these softwares. And second aspect that is like most difficult for everybody is the meshing. How to make the mesh, number one. Second question is that how fine your mesh should be then, and that aspect you have to like decide about your tetrahedron meshing or hexa meshing should be done. Then the what should be the cell size on different surfaces, what should be the inflation, how many inflation layers should be there, what should be first cell height, what should be the number of total layers in the boundary layer, how to decide about that thing, what should be y plus value, what turbulence model you are going to run based on that mesh. So for that particular turbulence model, which mesh should be there. So these things are discussed here, not only the meshing software itself, but the meshing aspects also. Okay. And then we set up the problem, and definitely we will go through the different aspect of the CFD solver. For example, the flow models like turbulence or laminar, transient or steady state, what should be done for turbomachinery, what should be done for the, like if there are some shock waves, material properties, how they can be decided, solver settings. So there are different solver settings that are important for the different problems, and they should be set on according to the each and every problem. Okay. And how you can judge the convergence, how you are going to initialize solution, and why you initialize solution this way, and then finally you have to run the simulation, and then finally you have to post process the results, and then you have to validate your results. So there are two aspects of the your results. One is a verification, and second is validation. So verification is based on the whatever the CFD theory says. For example, you have to create three meshes. You have to be running the second order schemes. So they are based on the CFD theory, that how solution should be done in the CFD software. The validation is you are comparing your solution with some analytical solution, maybe some experimental solution. So there's a validation part. So it may be we can expect the 10% or more than error in some problems, but that is the part of the simulation. Verification part is very important. That you should be applying all the good practices of the CFD. Mesh should be done in this way. Flow scheme should be selected in this way. So this should be done in a first priority. Then comes the validation. Okay, so okay, this is like a general introduction of the problem, and we will go through this problem right now after some time. Okay, so now first thing is any questions, any problem, anything at the moment? Any issue, please let me know, or we can continue. It's okay? Okay, so for this problem, we have the very simple geometry, very simple geometry. So we will solve the flow in circular pipe at Reynolds number is equal to 100. Okay, so this is the statement of the problem. And from here, we have to develop the solution actually. Okay, so first thing is that what should be your geometry? So in the geometry in the pipe, there are two parameters, two dimensions. One is the length, and second, the diameter of the pipe. So the first question is that what should be these two dimensions? So we discuss about these two aspects, the length and the diameter. And then definitely we have to be putting some velocity here. So what should be velocity here at the inlet? Outlet is always, in the most cases, outlet is like a pressure outlet. And the pressure is the pressure that is it will be experiencing when the flow is exiting from there in the atmosphere. So we make the length so it's a large, so that it will be like having pressure that is equivalent to the pressure it will be experiencing at the atmospheric condition. So usually speaking, for the sea level condition, this pressure is a 101.325 pascals. Okay, and there are two things in the pressure definition. One is the gauge pressure, and the second one is your atmospheric pressure. So atmospheric pressure is called as the operating pressure in the fluent. So in the fluent, they call this operating atmospheric pressure as the operating pressure. So actually what is going to be there in the CFD software, that the pressure you are going to get is the absolute pressure. So in the solution, but you specify these two pressure, gauge pressure and atmospheric pressure or operating pressure separately. So, but the Fluent will be like, will be using the absolute units. Like for temperature, it will be using Kelvin. For pressure, it will be using the absolute pressure. So this is equal to the sum of the gauge pressure. The gauge pressure is the pressure that you are going to measure with some device, any pressure gauge. So gauge pressure plus the atmospheric pressure. So in this case, what is going to be pressure here? Actually, this pressure will go into operating pressure. Okay, this will be the operating pressure. And here we will be defining the gauge pressure here on the pipe outlet. So this whole pipe will be having the same operating pressure, which is the 101325 Pascal at sea level. But at the outlet, the gauge pressure would be equal to 0 pascals because there is no pressure actually over here. No extra pressure is over here. Whatever pressure is from atmosphere is there, so gauge pressure is the 0 pascal. And at the inlet, the pressure will be from the like energy you are inputting there, that is from the velocity. So that is going to be the 1 upon 2 rho v square. Okay, 1 upon 2 rho v square. This is the like dynamic pressure. Okay, this is coming from the some source. So this source can be the some pump is pumping the flow inside the pipe. This can be the like from the fan in case of the flow your fluid is the air. So fan is pumping the air inside, or this may be pump in case of the water or liquid. So this is coming from that external source. So we are not modeling that external source. So we are applying that pressure whatever we are getting from that particular source. So this pressure will be dropping throughout the pipe. So this will drop to the zero gauge pressure from the starting of the beginning at the inlet to the outlet. Okay. Okay, I think this is clear. Any questions, please let me know. Okay, so for CFD simulation or for the even for analytical solution for experimental work, we actually need the 4 parameters. That is combined in the Reynolds number. That is the density, velocity, the dimension of the your length dimension of the important dimension of the your flow in your particular geometry or your particular case, and the viscosity. So these are the fluid properties. This is the flow property, this is geometry. And one more thing is that there's no need to be specifying the some particular fluid in the CFD, because in the actual life we cannot be putting the some arbitrary values for density and viscosity, because we have to choose either air, oil, hydrogen, argon gases, or these like this. So they have the particular properties. So we have to put like those in the wind tunnels or the lab scale. But in the CFD, we have the benefit, like we can even put the temperature of like 10,000 Celsius. Nothing will happen in the computer simulation, okay? But in the actual practice, this is not possible, or possible when we have the some, we can control our conditions there, material properties, materials which we are going to use, they can sustain this much temperature. We can sustain that much temperature at that particular location. So in the actual practice, they are difficult to achieve, but in CFD, we can apply anything like that. So density and viscosity can be specified independently. And the goal is that the Reynolds number should be matched. And if you are running simulation on your side, I am running simulation here, the only thing is that Reynolds number should be matching. And then the simulation will be similar. Okay. When we have the same Reynolds number, simulations will be, our case results will be similar. Anybody can tell me what is the meaning of similar and what is the meaning of same? What is the difference between similar and the same? Anybody can explain what is the meaning of similar and the same? And both are same thing?
I think in case of similar, the results will be following some pattern, and if we talk about same, so the results should be exactly alike.
Yes, correct. So in the similar cases, actually in the similar, we actually, the flow properties are the flow features will be same, they are same, but most important thing is that the non-dimensional parameters will be same. Non-dimensional quantities will be same. Okay. For example, we have the wall shear stress. That value can be different for different properties like velocity, viscosity, and the density. But the coefficient of friction, which is the CF, which is equal to the wall shear stress divided by 1/2 density into velocity square. So this will be the, like, they will be the same values. Okay. So similar values, when we say similar values, the solution will be same, the pattern will be same, but these non-dimensional quantities will be exactly same, but dimensional quantities will be different. Okay. So I think this is clear. So from this Reynolds number, we have to we have to find out the flow regime, the laminar flow or turbulent flow, and then we have to find out these properties that we are going to input into the CFD simulation. So density, viscosity, velocity, and the length. In some other cases, maybe some other parameters. For example, for wind turbine simulation, we have to also find out the RPM. Okay. Okay, so this is now we are going to go through the theoretical analysis, and please let me know if you are comfortable, if I can send you the slides. I can switch to the CFD side. If you are not, then I can be explaining this theoretical part over here. Okay, so first is that for internal flow, if we are talking about the pipe flow, so if the flow is laminar or turbulent based on the Reynolds number, we are not going to expect. We will go in the next slide. But right now, the only one parameter that will be deciding the flow nature of flow is the Reynolds number. So for the internal flow is laminar if the Reynolds number is less than 2300, and the flow is turbulent if the Reynolds number is greater than the 4000, and between the 2300 and the 4000, the flow is transitional. So you can see here that when the flow is coming from the top, this is almost a laminar flow over here. Okay, here flow is like a changing to transitional. Some part is like a laminar, some part is like changing to turbulence. So mixture of laminar flow and turbulent flow there some a small burst of turbulent flow makes the flow transitional. And definitely here the flow is very much disturbed flow. So this flow here is a turbulent. Turbulent, here I can say transitional. And here flow is a laminar. And then you can see the both way, it will be giving you the turbulent flow, but outside you can see the flow is very calm. And here in these locations, flow is like a laminar. Okay, so based on the looking at the flow, you can see that if the flow is disturbance, then flow is turbulent. No disturbance, then flow is the flow is the laminar. And but that's difficult to say actually in the different cases. So the Reynolds had given there is the one experiment you can search on the YouTube, that you can search on the Reynolds experiment. So it put the die there and then put on it changes the velocity, and then he sees that as the Reynolds number is increasing, because the velocity will increase, is increasing, then the Reynolds number will also increase. After a certain value, the flow start to behave in a disturbed way. It is like not following a lamina. So lamina is a laminar then. Okay. So that's why we have so based on those experiments, we have the one parameter, mathematical parameter, so we can decide about the flow is laminar, turbulent based on the Reynolds number. So definitely for our pipe flow, the flow is laminar because Reynolds number is less than 2300. Okay, so here you can see that the flow is like a start in the beginning of this geometry. The flow is laminar. When it gets disturbed on this expansion part, the flow becomes turbulent. And similarly, you can see here is a combustion of the fuel. So initially the fuel was going in a laminar way, even including flame. And then the flow is changed into small droplets and then into the vaporized. So you can see the now flow is disturbed, and this is a turbulent flow here. Okay, so then I thought that I should be giving you the definition of Reynolds number and the formula how it is derived. So Reynolds number is defined as the ratio of inertial forces to the viscous forces. So inertial forces that you can find out from the Newton's second law. F is equal to ma. So this is the inertial force, that is because of the velocity or momentum. Viscous forces, you can get it from the Newton's law of viscosity. So viscosity will always will make the flow as a laminar. More viscosity will make the flow go in a particular order. For example, this is cylinder, okay, two-dimensional cylinder, and we have the external flow here. So if the flow is laminar and viscosity is very high, then the flow will go in this way, and it will behave very nicely, and it will go like this. Okay. In case of the viscous effects are dominating. But the actual thing is that you can see that there is a lot of like slope here. From here, slope on 90 degrees here. So you can expect that the flow should be separating from the this point or this point depending on the Reynolds number. So that's why as we go with the higher Reynolds number, you will see that the flow will be like detaching from the some location. So it may go like this way. Okay, it may go in this way also. So depending on the Reynolds number, maybe it will separate from here. It will separate from here. And we can find out this location exactly on the circular cylinder based on the coefficient of pressure value. So if the values are okay, means that they are not having dip and then have the straight line, then it indicates the flow separating. But if they are behaving in like proper nature, like the flow is now here, if the velocity is decreasing, the CP should be like it should be decreasing. So CP increasing means pressure is high. Okay, so so inertial force is like a Newton's second law, mass into acceleration, and we know that the density is the mass divided by volume. So I can write down the inertial force as the mass as the volume into density, and velocity upon time is acceleration. And then from here I can write down the this density here, volume here, but time from the velocity I taken out and put it on the under the volume. And this is the velocity here. And also you know that the volume flow rate is the volume upon time, that is the in SI system is a meter cube per second. This is the area, this is the velocity. So area into velocity will be same units, meter cube per second. So now I can put this formula as the density into, now this is the volume is the volume flow rate is this is the volume upon time is the area into velocity into velocity. So inertial force is the rho AV square. So inertial force is the rho AV square. Okay, so we have the inertial force here. Okay, so we have derived the formula for the inertial force, and now viscous force. Now viscous force, any force basically you have to multiply with the area. Its corresponding shear stress or the pressure term, because stress and pressure, they are the same units. The only thing is that how they're applied on the flow or on the in the solid mechanism, how they are applied on the bodies, but the units are same for the shear stress or for the pressure. Sorry, stress and the pressure. So force is like is a stress into area, and we know that the shear stress by Newton's law of viscosity is equal to the mu du by dy at some location, and because the slope is negative, so we generally speaking we put the minus sign here to make the quantity positive. But right now we don't need it, so we just go with the whatever the sign is over here. So it's a mu du by dy shear stress and into area. And now I can actually write down this du by dy. This is in the limiting case, but for the whole geometry, this will become the u, and this will become the length. Okay, dy will become the length. So this is a v upon L into area. So now I can put this whole thing into the formula: initial force rho a v square, and the viscous force is a mu v L upon area. So I can cancel out the area. I can cancel out the one velocity from the numerator and the velocity from the denominator. So we get the formula as the rho VL upon mu. So I told you this length is a characteristic length. This is an important length of the your flow flow on the your geometry. For example, if I talk about the backward facing step, okay. So for some Reynolds number, some properties of the fluid properties and the flow properties. Now flow is going like in this way. So as soon as it approaches here, this will separate from here. and it might attach over this point. This is like a separation location, and this is the reattachment location of that flow. But now if you decrease the height, let's say if the height is decreased to this level, okay, so for the same flow, the attachment point will be different. So for the same flow, this might be different. So this might attach over here. Okay. So definitely in this case, the length of the step on the downstream side or the length of step upstream side, they're not important, but the height of the step is important. So here, maybe in calculating Reynolds number, you can put instead of the length, you can put the h over here. Okay. So for the pipe flow, the diameter is important. That's why we're putting the diameter here. So for pipe flow, for our case, the Reynolds number formula is the density times velocity times diameter times viscosity. And the units are for density, units are the kilogram per meter cube. This is the SI system. Velocity in the meter per second.
Sorry for sir, one question.
Yes, please.
Sir, actually, like how actually we assume this L by D ratio? Like this is my question.
L by D ratio, this is we are going to cover. This L by D ratio, for that I have the separate discussion also. Okay, that's the important point. So this is coming like over here.
In this lesson, sir?
Yes, over here.
Yeah.
Okay.
Okay, sir. Okay, sir.
Okay, so I think, yes, please. Anybody else?
Sir, we do just theoretical lecture, or there is like ANSYS simulation?
ANSYS simulation is definitely going to be there. So first I'm going through the theoretical part, and CFD part is starting here. And my point is that why we are doing this thing, because in your undergrad or in the master's studies, you always concentrate on the passing out your paper, but you might not have gone through these parts in this way. Like Reynolds number, you know about Reynolds number formula, but you might know or might not know how formulas derived. So, and what should be the when we talk about Reynolds number, we get this formula. So question is that the length, length should be decided here. So these things are important, because whenever you want to solve the CFD problem, so you must know these things. Without that, those things, those basics, you cannot solve your problem. Actually, you can run the software, but then your understanding level will be very low. For example, you can copy some tutorial from YouTube, and then you can apply in your problem. But whenever you run into problem, you will never know what thing is causing the problem here, and what should be the solution there. So if you know the basics and the inside out of every problem, every field, so you can understand what is the actually problem and how you can overcome that problem. So these aspects should be there. For example, I have solved the problem on the backward facing step. Okay. So people say that a Reynolds number based on the height, the flow become turbulent after 800 Reynolds number. Okay. And when flow becomes turbulent, they also say that we cannot run the simulation as a two-dimensional. So we have to go for 3D case, not the 100% 3D case. It should have some enough third dimension so that the flow can make the vortices, and vortices can cross. They can go in the third dimension. They can cross. So they are not always going in the 2 dimension, but they can also go in the third dimension also. So let me show you one thing. Might be this will clear your idea. So I have the one simulation with me that can show you this thing actually. At one time, I have designed a wind tunnel for somebody, a wind tunnel. So now wind tunnel, how we can test the wind tunnel? So what I did is that I put the one cylinder inside, circular cylinder. So we know that for that particular circular cylinder, what should be the value of the drag coefficient and lift coefficient. So if you put that cylinder into our wind tunnel in the numerical wind tunnel, like in the CFD, so if you get some results, those results should maybe matching with the actual wind tunnel testing. Okay, those we know that thing. So anybody who is making the wind tunnel, he does not have the wind tunnel. So how we can access the wind tunnel performance? So based on CFD, actually we can compare the known cases. And in that case, I have seen this thing that the problems are basically the flow is like it's a three-dimensional actually. So over here, you can see that the flow is actually is moving on the side to side also. It's not only going in the two dimension like in X and Y, but in the Z direction, flow is also moving. You can see the path lines are moving on the in third dimension as well. You can see the how flow is going. So this is the developing flow. Then the once flow is developed in the cylinder, it should be making the one carbon vortices. Now it is starting to make the one carbon vortex here. Okay. I can like show you another simulation. Yes. This is with the vortex also enabled. The flow is establishing. Now you can see the flow is going in the third dimension as well. So if you know these things, then you can actually you can solve the problem through CFD software. But then solving the correct solution, having correct solution or wrong solution, you cannot judge that the what values I have right now. So if you know the basics or inside out, which is like used in the even if you are making the analytical solution, you must know. If you are making the wind tunnel testing, you must know these things. You are making CFD simulation, you must know these things, and including the CFD basics as well. Okay.
Okay, sir. Like sir, one thing like I'm asking one question. Like, sir, what is validation? Like, I mostly heard this validation. Like,
Validation means that your results are matching to the some known data. Because, for example, now let me tell you the layman language. Okay, that let's say you are going to buy some grocery. Okay, and maybe there are some small kids in your home, and you send them to the market, and you say, okay, buy this thing for me. Okay, and the actual price of that particular item is, let's say, is 10 rupees, and your kid buys that thing for 15 rupees. So definitely there's a disparity between the both values. So you will tell your child, okay, no, this is not, and the person has overcharged you. So you must know your actual value or actual things there. So might be you can survey the market. You without knowing the data, you can survey the market and you can see, okay, few people are selling at this price and somebody is selling at 20 rupees or $20. So you know that the what should be the like expected solution or expected results here. But if you have the like a list from the some government agency, then you can exactly know what is the going to be the price of this particular item. So now if you are going to buy, then your price, your purchasing price should be close to this price, like maybe 14, maybe 16, 14.5, then you're close. But if you are going to be buying that particular item at 30 rupees, then you are actually having the lot of difference here. In the same case here, for example, if we have the like a NACA 0012 aerofoil, and we have the drag coefficient for the NACA 0012 aerofoil is 0.02 or 0.005, let's say. And your CFD simulation, you are having data as maybe 0.05. So the error is lot of there is it's almost like a 10 times more error in your simulation. So when you run the like you set up the case, so now maybe you made the geometry in a wrong way. Maybe chord length is different. Maybe the aerofoil is different. Maybe the geometry you made, the domain ATC is not the correct one. Maybe your meshing not correct one. Maybe you have set the not the proper settings in the CFD software. Maybe your reference values are wrong. So once you set everything correct, because CFD software is like a cockpit of an aircraft that you have to know everything and in a particular way. So they should set in the particular like a ratio. Otherwise, you cannot get the correct solution. So once you know how to set up these things in a proper ratio, then you should be getting results which is close to like a, maybe not 0.005, but at least 0.007. Or maybe sometimes maybe your results is like a very off, like a 0.009. But you know that this much error is there. And I have run the simulation NACA 0012, and I was getting results like with the error of 50%. And I know this error is expected for RAN simulation with fully turbulent simulation. This error is expected 50%. So either you know what is the problem actually, and can you improve or not. So these things we should be knowing. You should know very well. So this is validation. Okay.
Okay, sir. Thank you. Jazakallah.
Okay. So now let's back to our problem. So we discussed about this thing. So now few more lines on the turbulent laminar flow. So when you see the flow in a line or lamina, okay, so the lamina flow is going in a line. So and some small disturbances are there, but they will be quickly damped out because of the viscosity. Viscosity is very high, and inertia is less. So those disturbances will be damped out quickly because of the very high viscosity. So flow will always remain the laminar flow. But if the flow is laminar, but there are some continuous like burst of the turbulence. Okay, there are some intermittent means with some time with over the time. So in the some time after some time, then flow is like a behaving in a proper way. Then again we have some disturbances. So these occasional disturbances are the turbulences. They will be there, then they will make the flow as a transition. That means that sometimes flow is laminar, sometimes flow is like a turbulent. But once those disturbances grow and the viscosities are not able to control those disturbances, then the flow is a turbulent. Okay, the flow is the turbulent. So one thing I think made a mistake here. Should go over here. Okay, now this is correct. Okay. Okay, for external flow, the definition of laminar and turbulent flow is slightly different based on Reynolds number. So for external flow, if we talk about the single number, then this is like 0.5 million Reynolds number. So flow is laminar when the flow Reynolds number less than 500,000, and the flow is turbulent when it's more than the 500,000. But in the actual practice, actually we have this range. Like we have that for internal flow. For this range of flow is transitional. For less than this value, flow is laminar, and greater than this value, flow is turbulent. But if you are like going through the obstacle, like for example, there is like a tower here. Okay, if you are going around this tower, then this will like get disturbed very quickly. These formulas, these values are for the like a body in an atmosphere that is not going to disturb the whole flow. But only flow around that one will be going to disturb. Like we can see the turbulence here. So for obstacles like these ones, like towers, buildings, the flow will become turbulent at Reynolds number greater than 20,000. Okay, and one more thing is that you can always make any flow turbulent by putting some disturbance here. Like you throw the stone or the rock in the water and the very calm water, you can make the flow turbulent for some time. Then they will be dampened out quickly. But for that instant of the time, the flow is turbulent. Okay, so disturbances can also cause the flow to become turbulent, and then the Reynolds number range will not be useful in that case. But in our CFD simulation, actually we are not putting any disturbances here. Okay, so we are running the very smooth solution. We are putting the domain proper way. We don't put any rocks there in our CFD simulation. So that flow is like you should be following these numbers then. Okay, any questions?
Doctor, you denote the units of lamina?
The which one?
I think probably before you went to another slide, you were talking about deriving the units of lamina flow. I think slide number.
This
previous slide before.
No, this one.
Yeah, you are there. Then before you finish on the units of lamina, I think you went allowance number. You went to talk about things else. So what are the units of allowance number?
What is the value of Reynolds number or the importance of Reynolds number? Can you please repeat?
Yeah, I wanted to know the unit I think you were driving the unit.
The units for the Reynolds number.
Yes.
Okay, no, sorry, I didn't mention it. The Reynolds number has no units.
Okay, thank you very much.
Okay. You can check it from the this is the Reynolds number is density is a kilogram per meter cube. Velocity is meter per second. Length is meters. And the viscosity, we have the two type of units, Pascal second also, and one more unit here. I don't remember directly, but I can show it from the, I can show you from the slides here. So I think one is the kilogram meter second. If I remember correctly, one is a Pascal second. They are exactly same units. So kilogram per meter second viscosity. So this is from the pressure Pascal and second. So you can drive this unit also. So like here, if you put these parameters, these dimensions into the formula, you will see that they will become the non-dimensional. So if I put the here kilogram per meter cube and the meter per second and the meter here, viscosity is a Pascal second. So I can like drive the Pascal second is equal to Newton per meter square into second. Okay. So pressure is in the Pascal is in Newton per meter square. So from here, the Newton, 1 Newton, this is equal to the 1 force is equal to MA. This is like equal to the kilogram meter per second square. So divided by the meter square into second. This becomes the, we can cancel out the 1 meter from here and 1 meter here. So 1 second from here, 1 second from here. This becomes the kilogram per meter second. Same unit I've shown you, okay? So now we put this thing over here, kilogram per meter second. This is also second. You can write down the second, only S, but sometimes I think this is clear to write down the SEC. But generally speaking, in the books, this is only written as a S. So now you can cancel out the kilogram from here, second from here. There is the, like a meter will go on the top side, there will be meter cube. Meter cube will cancel out. So no units. Okay. Okay, any question? Okay, so we will be having the 10 minutes break, and then we will continue at the exactly 8:08. Okay, at the 8:08. Sorry, 8:09. Okay, after 10 minutes. Okay, after 10 minutes we will meet again.
Thank you.
Okay. Okay, so ready? Okay, so let's start again. Okay. Okay, so now if you take a look here on the flow over the cylinder, not inside the cylinder. So for the non-number is less than 5, you can see the flow has no separation here. Why? Because the viscosity effects are dominating and the inertial effects are not there as such. For the non-number from 5 to 40, you will see that two pairs of the vortices in the wake, which are close to the body, but away from body, the flow is now again very smooth. And the simulation that you have seen, might have seen in the some YouTube videos, they are there mostly they are made in the non-number range up to the 150 or 200. So typically speaking, I would be making at the 100 to the 200. So what you are going to see is that you will see that the same vortices, but they will be like alternating. So from top and bottom. So one time the flow will separate from top, and second time flow will separate from the bottom. So you will get an alternating type of the vortices. So this is called as a von Karman vortex state. Okay. So I can show you one simulation on that particular case. This was actually solved on the Reynolds number is equal to 150. So let me show you some videos. Here you can see that the flow was initialized in a very different way, so that the solution can like converge to the water shedding very quickly. You can see that we have the two pairs of vortices. The one is separating from top and one is separating from bottom alternatively. So that's why you can see that the one vortex will hit on the top and this will get separated. So you will see the vortex straight going through the whole domain. But now in the in the CFD case, the mesh is very fine. Also over here, then you can see the very clear picture of the vortices. Otherwise, usually speaking, I don't make the very fine mesh up to the outlet because this will make the mesh as very large. So this much region is important. Is enough to make the animation properly. So this is like at this value of the Reynolds number. So you will see the vortex will be like separating from the top and bottom, and then they will make a street. From the Reynolds number 150 to 300, and then 300 to 3 into 10 power 5. Now this is the lower range of when the flow is laminar. Okay. So what you are going to see is that the flow in the boundary layer is the laminar here. So the flow is laminar, but in the vortex state, the flow is turbulent over here. And then in the transitional region, which is like 3.3 10 power 5 to 3.5 10 power 6, in this region, the flow has no water shedding. Okay. Similar to the problem over here. Sorry, this one. Okay. And after that, when the flow is fully turbulent flow, we call the flow as fully turbulent when it doesn't have any part of the laminar flow. That is when the Reynolds number in terms of this value, this was is more than 3 10 power 6. So two things. The vortex state is turbulent, like you can see this flow. Okay, you can see over here. Okay. So here you can see the vortex state also is a laminar and so is a boundary layer. But here the vortex state is a turbulent and so is the boundary layer. So they are similar cases actually. And this case and this case is similar. And here we don't have any vortex state is here. Flow is very much disturbed and you cannot see any particular pattern over here. Okay, I think this is clear. So now we move to our actual problem and theory. So in the pipe flow, what is going to happen actually, that we have the like flows entering at the as a uniform flow at the inlet, and when the flow goes along this edge of the wall, so at this point the flow is like you cannot see the this region here actually. So this pipe on the wall, they might have the very small disturbances there. So they will look like in this way. So on the pipe surface, actually, if I zoom it, you will see that the pipe surface will have the some roughnesses, some wavy region here. Okay. So any particle which will be in the contact with this region on the pipe. So from the if you take a look from with your bare eyes, you will see that it's a very smooth. But if you go on the microscopic level, there will be some roughness on the your geometry. This is the roughness height. You might have heard about this thing epsilon. So there's some roughness in the pipe over there. Okay. So any particle which is trapped here will be stick to the wall of the cylinder, and the velocity will suddenly become the zero. Okay. So as the flow is entering there, the velocity is is uniform here everywhere, so it's equal. And but as it is attaching to the wall of the cylinder, or any case in any case, whenever flow is like passing through the wall, it will have the same behavior, and this is known as no slip condition, because the flow cannot slip here. So as we have the holding mechanism here, so that's why we call this condition as a no slip condition. So then it will be like growing in the boundary layer, and finally it will grow where the whole flow will be in the boundary layer. Like we have the parabolic velocity profile, and now complete flow is in the inside the boundary layer. So at this point, we actually call the flow is fully developed. But you can see a few things here. You can see the velocity here is zero. And this point, the velocity is maximum. And now question is that what is going to be the average velocity here? So you know that at any point, the flow rate should always be the same. Okay, flow rate cannot be different. This is the conservation of the mass. So flow rate should be same. And for this simple pipe flow, there's no area change. Area is constant. Flow is incomparable, so density is also is going to be the constant. So only thing that is changing is the velocity. Now thing is that the velocity cannot change actually when the flow rate is constant. So how the velocity changing? The velocity changing because of the boundary layer. So it has to have the some velocity that is going to be like, if you average the velocity over the whole radius, it should be equal to the, if you average over this radius, it should be equal to the average velocity. That's why if you average out the whole velocities like these values, then you should be getting the velocity that is equal to the what velocity you're putting into the at the inlet. So that's how you find out the average velocity here. Okay. So now the problem is that we have to actually find out the in the pipe flow, we have to find out this profile. We have to find out the pressure over inside the pipe. We have to find out actually also the VAWT shear stress or shear stress at any point. We have to find out the maximum velocity. We have to find out the average velocity in the pipe anywhere. This is all we are going to do here. Okay. So we must be looking at the entrance region when the flow is developing and the flow is then developed. And please keep in mind that all the theoretical formulas, all the analytical formulas, they are applied in the developed region. So when the flow is developing or the entrance region, these formulas which we'll see theoretically, they will not be applicable on the region over here. And that's the point that we have the CFD tools, because CFD can predict this region, but the theory cannot predict this region over here. Okay. So we will see that how pressure gradient is coming from CFD and how pressure gradient is coming from the analytical results. What is going to be value of the shear stress from the CFD, and what is going to be value of shear stress from the theoretical values. And velocity maximum at the center, we will also see this thing. And when the flow is fully developed, so how we will be accessing that through CFD, also we'll look into these things. Okay. Any questions? And if you have any questions, you can put in the chat also. Okay. Any questions? Okay, thank you. Okay, so first thing is that if you take a look on the continuity equation in the cylindrical coordinates, you will see this equation. Okay, and please keep this thing in the mind that for the pi flow, what we are going to see here is that in the pi flow, if I draw the pi flow here, so in the pi flow, you will see this thing. This is very much, I think, very obvious here that in the case of pi flow, you will see the few things here. Number one is that velocity cannot go in the normal direction, like in the radial coordinates. So the radial velocity is 0. Also, we are assuming that the flow has no change across the angular coordinates. So it means that the u theta is also equal to 0. Okay. So only velocity we are having, and this is a very simple case that if you enter from here, so only way that you can go out is the axial direction. Okay. So only velocity we have is the axial. So we denote that axial velocity by the x. Why we do this thing? Because in the books they have the 3 coordinate system. One is the Cartesian, and they have the coordinates like x, y, z. So you can see if you apply the Cartesian coordinates here, you will see the x here, y here, and z is along the length. So this is like y, x, and z along the length. And in the cylindrical system, they have the axial, radial, and angular coordinate. So for the cylindrical system, they have the r, theta, and the x. Instead of z, they write down the x. But don't get confused. This x is not same as this x. This x is along the axial direction. So these local coordinates on the circular boundary here, they are the local x and y, but the axial direction is like this one. And then for the case of the spherical, they have the 3 different r, theta, and the phi, 2 different angles. Okay, so question is that why we are using the cylindrical coordinates? Because we can simplify our problem to 2-dimensional very easily. How? See, when I say that there's no velocity in the theta direction, there's no velocity in the r direction. So only velocity that is important is the axial velocity. Number 1. And number 2, there is no variation along the angular coordinates. So it means that the rate of change with respect to the theta is 0. Any quantity with respect to theta is 0. So the theta is now out of the equation, out of the scene here. So only thing we have is the r and the x. Okay. So we have the r and the x. Or you can, for some time, you can just make it like x is as a z. Okay, z axial. So actually, if you go to Cartesian, even if you remove the angular coordinate or theta coordinate, r does contain the x square and the x and y both. Okay. So if you are in the still you are in the coordinate system, then you have to deal with the 3 parameters, 3 variables. But if you shift to the r and theta to cylindrical system, you will only be dealing with the r and the axial. It means that now you have simplified the problem to the only 2 dimensions. So from 3-dimensional problem, you can only solve like this is a 2-dimensional problem will be solved in this way. So you take the one plane from the axis like this. So if you want to solve this problem as a 2-dimensional in the Fluent, then you have to use this plane from axis, not up to the bottom. Okay. So this boundary will be defined as the axis, and this boundary will be inlet, like normally in the 3D case also. This is the outlet, and so outlet, inlet, and this will be the wall, no slip wall. So only extra boundary condition that you are solving in the 2-dimensional, in the Fluent has the option to solve case in 2-dimensional axisymmetric. So this is going to be axis. Okay. So actually this solution and from 2-dimensional axisymmetric problem and 3-dimensional simulation, they should give you same results. Okay, they should give you the same results. So I will be teaching you at the end of this workshop also, I will teach you how to make the geometry for 2-dimensional case and the meshing also and simulation, and then compare the 2-dimensional and 3-dimensional results. Okay, so now we know that we have the no variation, there is no component of theta and the UR. So only velocity we have is the axial. Okay, so that's why you can see the UR is 0, the U theta will be 0. Only thing we have right now is this is like for the axial velocity. Okay, so axial velocity derivative is constant, 0. So this shows that the velocity at two locations will be same. There's no variation of the velocity with respect to the Z. So this implies that the velocity variation is only along the radial direction. So actually there are two forces. One is a pressure gradient. That gradient is along the x direction. And then we have the velocity gradient that is along the radial direction. That's why we get this boundary layer. So this boundary layer, like this flow is the force that is up. This is inducing the flow here is this pressure gradient from inlet to outlet. Okay, so obviously this from there you can see that the velocity is only function of the Z. Now, if you take a look on the momentum equation in the coordinate system, I would suggest one thing, that you can go through this book. This is a book by the Frank and White, and also I put the same book in the group, so you can download it from here. So if not, I can upload the book again. I think this is gone on the upper side of the chat. So I can upload this book again. Okay, so you can download from there. Okay, so here you can actually you can find out those equations for the momentum and the continuity, momentum, continuity, and also energy equation. So here is all things are given here. So you can go there, you can find out from the table of contents, you can find out those equations, or you can write down here in the search bar momentum equation. $155. From here actually. And the second book that I would suggest is the Fluid Dynamics. It has like a more clear derivations for continuity equation and the momentum equation, energy equation. The Fluid Dynamics by Sengel. Okay. So anyhow, so we go to back to the Cartesian equations for x component, y component, z component. So these equations shows you the few things here. Number one, this is in the x component, we have the like x, we have the u velocity. Velocity in the y direction is denoted by the v. So this is actually depends on how the different books treat them. So z direction will be w. Sometimes they write down the ux directly, uy and the uz. Okay, so they instead of using the uvw, they directly use the ux, uy, uz. So it depends on the book and the author. So the first component is a transient component. Okay, so it's when you are solving the flow as a unsteady. So this term will come into play. So you have to just choose from CFD software as a transient, and this term will automatically be used in the CFD simulation. And these three components, they, like you can see now, you can check the order. Velocity is u, velocity is u, velocity is u here. but the derivative is with respect to x, y, and the z. And whatever the direction is there, the same velocity is multiplied there. So x, u, y, v, z, w. Okay. So these are the convection term. Convection term. Okay. So now let me tell you that what is the meaning of convection term. Maybe this is useful to you. Let's say we are inside the pipe. Okay. A pipe here. So let's say I'm moving there. So just 1 minute. Okay, so let's say I am right now, my flow is at this location. Okay. And then it moves to second location, which is like at this point, which is like x1 and the x2. So now you know that when we have the acceleration or the velocity, there is a change of, like, for example, velocity is the change of the distance with respect to the time, the ds by dt. Okay. So you understand this thing, that this is like might be dx by dt. So it is anything which is moving, it should have some change in the time. Okay. So that is the is a transient component. Okay. So if you move from one point to second point, that should be done in the time. But the second thing is that in the steady state cases, how the flow will move from the one point to second point. Actually, this will move from by the help of the some external force. So that, for example, you are sitting here right now at the moment. Okay. Somebody is going to hit you, like in case of some accident, some vehicle is hitting your vehicle from the rear side. Your vehicle will move. Even your vehicle is not moving, actually it's stopped there. So this is basically moved because of the some external force. Similarly, we can see that everything is multiplied with the velocity. So this velocity actually is the coming from outside. Okay. So it will move by this velocity. So this, the mechanism here is not time but the velocity. Definitely the velocity will contain the time, but right now this is like a steady state case. This is like a positional vector. It's changing. It's not changing because of time, but it's moving, changing because of the position vector, because of the velocity. This term is known as a convection term. Like we are putting some velocity, this converting from one location to second location. So this is different from this transient term. And here we have the pressure gradient. So definitely this pressure gradient will be like in respective direction. This will be x, here will be y, and here will be z. Okay. So pressure gradient is there, and then we have the body force. So right now the body force here is because of gravity. Right now the body force is gravity. So gravity, like if you are the flow is flowing from the pipe from top to bottom, in that case this will have some gravitational effect like rho gh. But in straight pipe, I don't see that the other forces are very, very strong there. So might be body force may not be important. So if you want to include the body force, like in the multi-phase simulation, we always do it. So we have to enable the gravity effects there. So and body force will be applied on the whole body. Like if the pipe flow is there, and if you turn on the body force like gravity, so this will affect the whole volume inside the pipe. So body forces will always be on the whole volume. So other example of the body force is the magnetic force. So magnetic force also is a body force. Okay. So these are the different terms here. And the last term here is this term here. This term has two things here. They are stresses. So any velocity with respect to same component, same dimension will be normal stress. And normal stress is not important in the fluid dynamics. Usually speaking, their values are very, very low. So only important values are the shear stresses. So velocity is in the u direction, in the x direction, like a u velocity, but gradient we are taking in the y direction or z direction. This is like a cross derivative, and this is shear stress. So these two terms, they are the shear stresses. Here, the normal stress is over here, and these two are the shear stresses. And similarly here, these two are the shear stresses, and this one is the normal stress. Okay, so now in the very like a simplified equation with no extra forces, we have the density is multiplied because flow is incompressible, that's why density is outside. So we have the transient component, we have the convection term, we have the pressure gradient term, we have the body force because of gravity here, we have the normal stress, and we have the shear stresses. So now we have to see which components are important for our case. So now if you transform them or drive them directly in cylindrical coordinates, you can see the R component and theta component and the X component. So right now we're not writing this one as a Z, but this is actually is along the axial direction, which is the Z in the Cartesian coordinate. So that's why writing them R, theta, and the X. So now again, take a look here. You can see R component. Again, you can see that the U theta, U R, they are 0. And the velocity, axial velocity gradient, now this should be written as the ux actually, okay, ux here. So ux velocity, axial velocity gradient with respect to the z. So with respect to x and theta, they are 0. So velocity is u theta, u r. Velocity in the direction of the theta angular coordinate and the r direction, they are 0. We cannot have the velocity outside in this way. Okay, so u are 0, and there's no velocity along the angular coordinate because the flow is exactly same on the all directions, all the angles. So that's why u theta also 0. So you can see all terms will go to 0. U r is 0, u r is 0, u theta is 0, u theta is 0, u r 0. So and gravity is not there. So these terms also be 0. So you can see the pressure gradient is 0. So there's no pressure gradient along the radial direction. Similarly, there's no pressure gradient along the theta direction. It means that the pressure gradient is only along the axial direction, which is the x direction in this case. Okay, in a similar way, now if you directly go to x component, you can see that we can remove these components. There's no transient component. We are solving steady state case. Ux by ur is not 0, but ur is 0. That's why this component is 0. And in a similar way, u theta is 0 actually, and the ux divided by u theta is also derivative with the theta is 0, so this is 0. Ux with respect to x direction is 0, so that's why this is 0. Body force is 0, pressure gradient is there, and again these two components are 0. So we have only left with the pressure gradient and the shear stress. So you can write down this equation this way, and you can take out this term on the one side, and this will become positive. And because we have the only one pressure gradient, so we can convert from the partial derivative to the simple derivative, so dp by dx. And here we can also write down this one as a mu divided by r, and d by dr instead of the partial derivative, and the r dux by dr. So also we will be writing this dux as a simple du. So we know that we are talking about the velocity along the axial direction. And the boundary condition are very important here. So boundary condition, they are being applied here, that at the the coordinate system is like we have the center line is going through the center of the pipe. At this point, the small r is 0. And on the wall, the small r is equal to capital R. Okay. And when we have the 2r, which is equal diameter actually. So these are the boundary conditions. So at the r is equal to 0, we have the maximum velocity at the center. So the maximum velocity means that we are the du by dr is equal to 0. So at the r is equal to 0, the derivative is 0. That's make the velocity maximum there. And at the small r is equal to capital R, that is the wall of the cylinder, velocity is 0. So we have two conditions, that r is equal to r, capital R, velocity is 0, and capital R, small r at 0, where the velocity gradient is also 0. Okay, so now from here we have the this governing equation, and this equation is the most important equation. Okay. Okay, now I'm going to we are putting the pipe flow here, and I'm taking one strip from the pipe, and I have taken out this strip from the pipe and taken over here. So this will be like we have the wall shear stress here on the wall here. Okay. So we have the wall shear stress here. And this will always be moving, they will be acting in the direction opposite to the flow direction. So flow is going in this direction from left to right, and the wall shear stress will try to stop that flow. That's why this always will be in the opposite direction. So from this small strip, we have the wall shear stress, and this value, now this is only single value. It's only along the circumference of the cylinder. That's why this is only one value. These are not two values, but it's a single value around the whole circumference strip. So the area of the strip will be equal to the, like this is a dx. Okay, this is a dx. And this length, this is actually a circular strip here. So this, the length of this one will be equal to 2 pi r. Okay, this will be 2 pi r, and if you multiply with the dx, so this will become the area. So 2 pi r into dr. And okay, this is dx actually. This is a dx. So dx. So that's why we have multiplied the wall shear stress to make it force. So we multiply with 2 pi r into dx. So this will become the force units, newtons. And the pressure applied on this side will, and pressure will always be normal to the your flow. So that's why you can see on this wall, this will be normal to this flow, will be a positive value. So this will be pressure into area. So area in the case of pressure will be the cross-section area, which is pi r square. And on the other side, this will be acting on the, from the negative side, on the opposite side. And only difference we have is the delta P, dP. Now this dP is not always, this is not means, plus and doesn't mean that this is increasing. The dP is like a change. Now this change can be negative, this can be positive. So we're putting only change over here. If the value is negative, this value will be reduced by putting the minus sign, and this value will be reduced here. So if this is increasing, then P plus dP will be higher than the only P. Okay. So now you can like balance the force in the x direction. So these two forces, they are the negative, and this one force is positive. So that's why we have the pi r square P as a positive, and minus pi r square into P plus dP is a negative. And same is the case with the shear stress force. So minus 2 pi r ds into tau wall or shear stress is equal to 0. So this value into P will be cancelled out. So we only get the value minus pi r square into dP minus 2 pi r dx into wall shear stress. So here from here, we can cancel out the pi r square and single r from here, and pi here. So we can have the like a value as a minus r dP is equal to plus 2 dx into tau wall shear stress. So from here, you can write down the dP by dx is minus 2 upon r wall shear stress. So actually this equation will give you the relationship between the wall shear stress and the pressure gradient. And the wall shear stress, you know that this is equal to the viscosity, and always put the minus sign to make it positive. Okay. So, and we have the du by dr. Normally speaking, this can be du by dy and du by dr. So you should be careful about the vertical component, and where r is equal to r. So actually you are connecting the pressure gradient with the velocity gradient. Okay. So the shear stress component with the pressure gradient term. And then for the whole pipe, this delta x will be the length. For the whole pipe, this delta x will be the length, and dP will be the delta P is across this strip here. For the whole pipe, this will be delta P. And for whole pipe, this will be a length of the pipe. Okay. So that's why now you can write down dP as a, actually, but dP is always the final pressure minus initial pressure. So that's why we write down this one as a P2 minus P1. dx is a x2 minus x1, but delta P is like when we show the delta P pressure drop here. So this is always P1 minus P2. So that's why this dP will be equal to minus, if we take it common, minus P1 minus P2. So dP will be minus delta P. So that's why we're replacing delta dP with a minus delta P, and the delta x with the length for the whole pipe, minus 2 upon r. Wall shear stress will be same on the small strip or on the whole value. Okay, this will be same. So minus 2 upon r and wall shear stress. So we can now simplify this equation into the delta P is equal to 4L by D and the wall shear stress. So always you will see that the L by D is always in the pipe cases. So this is a very important ratio. And actually the L by D ratio will determine your flow properties, flow characteristics. Okay. So delta P is the 4L by D and the wall shear stress. So now what this formula says that we can let the pressure gradient with the velocity gradient. Okay. And secondly, you can, if you know the wall shear stress, you can find out the pressure drop. Or if you know the pressure drop, you can find out the wall shear stress without solving for the wall shear stress. Okay. Any questions?
I have a small question.
Yes, please.
If you go back to the momentum equation with the Cartesian coordinate,
Mm-hmm.
You was talking about d square u over dx square is the pressure.
This one?
Yeah, that's
This is a normal stress.
So what is the difference between the normal stress and the pressure? I thought they are like same thing.
Actually, pressure. See.
Okay.
Okay, first let me give you the very in the layman language. Okay. Let's say you are facing pressure from outside forces like from the your social life, from the outside people, from your maybe from inside your home, like your siblings or your father, mother. So they are pressurizing you for something. Okay, behave in this way, behave in this way. So what is the reaction of your body? Your body will produce some stresses. Okay, you will get into depression maybe. I'm just saying, not I'm saying you are in that state, but your body will respond to that pressure. It will feel a stress. So the stress is always from inside the body in the reaction of the pressure. So they are the same forces. They will be like pointing to the, like for example here, this is my cylinder here. Okay, and we have the gases here, and this will insert the like a pressure here. So in the response to this one, we will be having the stresses. They will be opposite to this pressure applied. Same values, but they will be like on the other side. So the stress is always as a reaction of the pressure applied forces. Okay. So stress always is the response to the applied external forces. There's a reaction. Actually, the stress is a reaction to the whatever is being happening around yourself. Same case with the mechanics. So anything that is being pressurizing things, this geometry, this will react by the putting the same force but in the opposite direction. Okay.
Yes. Thank you.
Okay. So okay, just 5 minutes break, then we will continue here. Okay. Okay. So I will come back after 5 minutes. Okay. Okay, so from this formula, because the wall shear stress is the constant value, it will not vary. So that's why it also actually pressure gradient is constant. We know this thing. So from here we can also find out wall shear stress constant, or from wall shear stress we can find out the pressure gradient will be a constant value. Okay, so now velocity profile. Now you can go through these nodes. If you want, I can actually drive also on the some extra sheet of the screen. So, but this is like we have the pressure gradient equation, which is like from here, this equation. So if we take out this equation from here and put over here, so you can see that the when the flow goes there, it will develop the boundary layer like this one. Okay, and the velocity will be maximum in the center, and it will be like a 0 on the wall, and the wall shear stress is is on the opposite side. So where we have the maximum velocity, wall shear stress will be 0. Why? Because at the maximum velocity, the du by dt. Please, anybody? So wall shear stress formula is the viscosity and du by dr. Okay. So at the maximum velocity point, the wall shear stress, because velocity is 0, gradient is 0. So wall shear stress will be 0 at the center, or the shear stress is 0. At the wall, because the gradient is infinite, so we have the maximum wall shear stress on the wall over here. Okay. So if you draw the wall shear stress, this will be like drawn as in this way, so 0, but it changes linearly, like here. Okay, but the velocity has when you drive the velocity formula, you see it has a square. So a square will make it parabolic in the shape. That's why it's a second order, it's a second degree equation. So you will see the parabola here. But shear stress has only one power in the velocity. So it's a linear profile here. So 0 in the center and the maximum on the wall. So from here you can like simplify, rearrange the equation. You can write down this as a 1 upon mu dp by dx, and the dr is on the top. So this is r, dr on this side, and the d into r du by dr, they are on this side. Okay, so we've taken the mu upon r and dr on this side. So now you can put the integration sign. The viscosity is constant, pressure gradient is a constant, so you can like integrate r dr, and this is derivative r du by dr. So this derivative will cancel out with the integration, and we just get the r du by dr on this side, on the right hand side, and this will become the 1 upon viscosity dp by dx and r square upon 2 plus c1. But here you can see the first boundary condition says that we have the at r is equal to 0, the derivative of u with respect to r is 0. So du by dr is 0. So if you put this value, this r is 0, this du by dr is 0, and this r is 0. So this will become the 0 plus c1 is equal to 0. So we can know that the c1 is 0. So equation 1 can be written as the 1 upon mu dp by dx r square upon 2 is equal to r du by dr. So again, we have the one derivative here. So we have to again integrate to get the value of the u. This u will be actually we define this curve here. This ur is a function that will define this curvature, this whole curve here. Okay. So you have to, if you want to find out this ur, you have to integrate this equation once again. So again, we can write down this equation this way, and then again integrate, and you will get the 2 mu dp by dx into r dr is equal to du. So du integration will be equal to simply u. And again, we have to put the integration constant, so you can like make it like a C2. Okay. So because C1 already used there in the previous slide, so let's make it C2. So now integrating this one will give you r square upon 2. So 2 will be 4. That's why we write down this as a 1 upon 4, and dp by dx r square and plus C2 is equal to, and this velocity is 0 at the wall, so that where the r is equal to capital R velocity is 0. So this is 0, and small r will be the capital R. So 1 upon 2 mu dp by dx and r capital R square upon 2. So this C2 will be like equal to minus 1 upon 2 into 2 will be 4. Minus 1 upon, if you take it on the other side, this will be minus sign. So minus 1 upon 4 mu dp by dx r square. And if you put in this equation number 2, you can get this formula. So now the mu becomes the minus r square upon 4 mu dp by dx 1 minus r square upon r square. But actually this equation contains these terms. Okay. And so if you want to like draw the velocity profile on the pipe, so you must know the velocities, the r and r. So r, we know that this r varies from 0 to capital R. That is the pipe radius, this radius r. And this capital R, we know that this is exactly what value we have. So problem is that dp by dx is not a known quantity. We can find out this quantity, but this quantity is not a known quantity. So there's no point having the unknown velocity and unknown pressure gradient. So we cannot find out the velocity from this formula easily. So now we have to change the formula in a way so that we can find out the velocity profile very easily. So this UR basis, U is basically written as a UR. So you have to change the value of R. So how R will be changed? For example, this is a cylinder, it's a pipe, and this is the center. And this is the R is equal to R here on the pipe wall, and here in the center R is equal to 0. So let's say the pipe radius is equal to 0.5 and diameter is 1 meter. So now in this case, the small r will vary from 0 to the 0.5. So like you can find out the velocity at this location, this velocity will be maximum. If you put the r is equal to 0, you will get the maximum velocity. And if you put this r is equal to r, and here at this point, you should be getting the velocity 0, because r square upon r square, capital R will be, this will be capital R, will be 1. So 1 minus 1 will be 0. So 0 into something will be 0. So this, from this you can get the velocity at 0. So if you want to plot the velocity profile in the Excel, so you have to write down the R here and the UR here. So why in this way? Normally speaking, we write down in the first column the independent variable along the x-axis, and the second column we write down the dependent variable. But traditionally, the way the plot we see in the books is like in this way, that the UR is drawn on the x-axis and R is drawn along the y-axis. So you have to put the value, like for example, the 0, 0.1, 0.2, 0.3, 0.4, 0.5. And you can use Excel for this purpose, which is very much easy. So for 0, maybe you will get the velocity as a 2 meters per second. At 0.5, velocity is 0. In between them, you get the different velocities here. Okay. And then you plot on the Excel and you will get the half profile. Okay. For the remaining half profile, like you have to vary the R from the 0 to minus 0.5. So you will get the full profile. And this half profile on the positive side and negative side, they're exactly the mirrored copies. So if you draw the 1, you can mirror in some software, but directly in the Excel, you can put the minus coordinates, and this should give you this value in this way. Okay, any questions so far on the velocity profile? Okay, so now actually the question is that how to find out the, because we know that when we are applying the velocity field on the pressure on the pipe inlet, this velocity is like a uniform velocity. So this is the U average. What about when the velocity once develop into the fully developed region, we have the boundary layer. So average velocity can be found out in this way. And this velocity is a velocity that should give you the flow rate that is like you are getting at the inlet. So it is given by the m dot is given by the rho u average, okay, and the area. So area is constant, density is constant. So u average, if you put this value over here, this is also constant. This should be same along the whole pipe length. Okay. So now our aim is to find out the maximum velocity and the average velocity in some known quantities. So now we have to transform this formula, this value into these two quantities, u maximum or u average. So you know that this is the velocity profile we have derived here. So we know that at the center of pipe, where r small r is 0, the velocity is maximum. So I can put this condition that the r0, u is equal to u maximum. So u maximum is equal to minus r square upon 4 mu into 1 minus 0, 1 minus 0, r is 0. So this capital R cannot be 0. This is the radius of the pipe. And dp by dx, so you get the u maximum is equal to minus r square upon 4 mu dp by dx. Okay, now in order to give you idea about the average velocity, I think that I should be putting in the OneNote. Then I can give you the better idea. Okay, let's make the new sheet. Okay, so what we're trying to do is that we have to find out the average velocity here. So average velocity. Okay, this is a pipe. And on the wall of pipe, we have the zero velocity, and the center, we have the maximum velocity. Okay, the center of the pipe. So R is 0 and R is equal to R. And here U is equal to U maximum. And here U is equal to 0. Okay, so now just for a time being, just think that we are taking the one strip here, a small strip here. Okay, so we are cutting it like in this way. So this will be like from the front view. From if you take a look on from the inlet, this will be like this strip here. So I can take out this strip here, and this strip will have the radius is equal to r. So this will vary from, definitely r is variable. So this will be like from here to here, this is the r. But from here to here, this is the differential of the r, dr. Okay. So this will have the dr here. Okay. So now let's say if I want to find out what should be the flow rate here. So this will be dq, the volume flow rate inside this whole strip here. So, and the area would be equal to what is the area of this? If I want to find out the area of the cross section of this strip here, which is over here, this area would be equal to the circumference into the thickness. So if I open it, this will be like the thickness will be the dr, and this length of when I open the cylinder, this circle, this will be like a 2 pi r. Okay. So differential area would be equal to the dA would be equal to the 2 pi r into dr. This is a differential area. Okay. But for the complete pipe, the area would be equal to what? Area would be equal to, for the complete pipe, because this will be whole cross section. So radius is capital R. So area will be here, will be pi r square. Correct? Pi r square, or if you want to find out the value in terms of diameter, this will be the pi by 4 d square. But what's for a very small strip, this will be the 2 pi r into dr. Clear? Okay, so now we know that in terms of the volume flow rate, the volume flow rate means that we are actually measuring the volume of the flow, that is a meter cube per second. How much volume is passing through some particular geometry. So in the whole pipe, how much meter cube or liters are passing in a 1 second. Okay, this is the volume flow rate. So it is written as the Q is equal to area into velocity. The formula for the volume flow rate is the area into velocity. So it's a meter cube per second. Area is in the meter square and velocity is a meter per second. So if you multiply, you will get a meter cube per second. Okay. And this velocity actually is a U average, it's average velocity here. So from here, I can find out the average velocity here is equal to Q upon area, right? Q upon area. Now, in a similar way, now we know that this strip will contain the how much flow? This will contain the very small flow that is equal to dq. For d area, and with the length of dx, actually, if you move it like in this way, the length of dx are the small length. This will contain the volume as a dq. Okay. So now I can write down this one as a 1 upon area. And if I integrate this dq from 0 to r for the full radius, this small elemental flow rate, volume flow rate, if I integrate this one from 0 to r, I will be getting again the q, capital Q. That is the flow rate we are going through. We're getting through the whole pipe. Okay. And I can write down this dq as this dq is equal to, now we know that the formula for the q is equal to how what is the value of the q is the area into velocity. Okay. So I can write down the dq as this will be the area. So u of r into the dA. Right. So from dq, we have the velocity function, and then for area, we have the dA. So if I want to find out the q, that q will be equal to the integration of 0 to r, this dq. This is equal to the 0 to r, ur, and the dA will be equal to the 2 pi r into dr. Clear? So now I can find out this U average by this formula. We have the area of the whole pipe is a pi r square. And 0 to r, and the dq is equal to the ur into 2 pi r and the dr. Okay. So now I can further put you know that the ur we have just derived, this ur is equal to what? Minus r square upon 4 mu. The ur is the minus 4 r square upon 4 mu, and the dp by dx 1 minus r square upon r square. So put this into the equation, minus r square upon 4 mu dp by dx, and the 1 minus r square upon r square into 2 pi r dr. Okay, so we can cancel out the r square from here, r square from here. We can cancel out the pi from here, pi from here. Okay. And we can cancel out the 2 from here, and the 2 will be only remaining 2 will be there. So what we have right now is the minus sign, 1 upon 2 mu, 2 into mu, and the dp by dx. And inside the bracket, we have the 0 to r, and we have the 1 minus r square upon r square, and into this small r here and the dr. Okay. So then finally we have the minus 1 upon 2 mu dp by dx and 0 to r. If you multiply this r with the bracket, this will be the r minus r cube upon r square and dr. So now integrate this equation. It's a very simple equation. So this becomes the minus 1 upon 2 mu dp by dx and 0 to r. So this will be r square. Sorry, if you integrate this one, this will be the r square upon 2 minus r power 4 upon 4 r square, and limits are from 0 to r. So minus 1 upon 2 mu dp by dx, this will be the like R square. And if you put a zero value, this will be zero. So there's no point of showing that step. So simply put the R, capital R, this will be R square upon 2 minus R power 4 upon 4R square. R square and the R power 2 will be cancelled out and only R square will be there. So I can write down this as the, now if you simplify, this will be the 1 upon 2 minus 1 upon 4 will be 1 upon 4. Okay. And 1 upon 4 into 2 will be 1 upon 8. So minus 1 upon 8 mu and the dp by dx, and this will be the R square. This is the U average. And also we found out that the U maximum is given by the minus R square upon 4 mu and the dp by dx. So if I write down the equation for the like the U average, so I can write down this equation in this way, minus, sorry, simply write down this equation as a 1 upon 2 bracket minus R square upon 4 mu dp by dx. Okay. And this term is basically is the U maximum. Okay. So I can write down this one as a 1 upon 2 and the U maximum. And from here, I can write down that the U average, I can write down U maximum will be equal to the twice the U average. Okay. So now go back to our slides. And this is what I did here. So here you can see that I have integrated this whole thing. And now you can take a look here that the U maximum is equal to the how much? Minus R square upon 4 mu dp by dx. Okay. And what is the formula here? The U is equal to minus R square upon 4 mu dp by dx. So this will be equal to what? This will be whole thing will be equal to the U maximum. And again, U maximum is not a known quantity because on the inlet we are putting the velocity that is the U average velocity here. So that every velocity we are inputting the pipe, we know that value. So again, we change this value U maximum into U. You can find out the U maximum from the U average, but directly you can put the U average in the formula. So that's why first we change to the U maximum, and we know U maximum is twice the U average. So here you can see that we can put the formula as a U and U maximum this one. So UR becomes a U maximum into 1 minus R square upon R square. And also the U maximum is twice the U average. So you can have the formula UR is equal to twice U average 1 minus R square upon R square. In a similar way, like we have the equation dp by dx minus 2 upon R wall shear stress, you can find out the velocity profile, this same equation from this equation up to this point. So you can also find out from this equation very easily. And then you have to do these steps again, like you have to find out the maximum velocity and the U average. So same formula you can also get. Okay. Okay, now the pressure drop formula. So you know that we have derived that the average velocity is equal to minus R square upon 4 mu, 8 mu and the dv by dx over here. The U mean value is, or U average value is the minus R square upon 8 mu dp by dx. So for the whole pipe, this value will be like a delta P and this dx will be the length. Only thing is that delta dp is equal to minus delta P. So minus sign will be cancelled out. So just see here that we have the U average is equal to minus R square upon 8 mu dp by dx. So we can write down dp as minus delta P. So minus delta P upon length. So this will cancel out and we get the 8 mu L U average divided by the R square. So I can convert the R square into the D square upon 4. So we get the 32 mu L U average upon D square. So this is the pressure gradient formula you see in the books. And now the last thing that I am going to cover in the theoretical part is the friction factor. And second is the Fano friction factor. So friction factor is the full name is the Darcy friction factor. Actually, what is happening here is that when the engineers, they started to study the water in the channels in the rivers. So they developed the a field of the fluid dynamics that is called as a hydraulics. So anybody who is has a background of mechanical engineering, he will understand that they study the hydraulics, not the fluid dynamics in a proper sense. And the people they are coming from the aerospace side, they are studying the fluid dynamics. That is they will develop the equation based on the air. Mostly they use the air as a working fluid. So they have the different terms and different way to represent the values. So in the hydraulics, they have the fraction factor, or you know that one as a Moody's fraction factor also. And second, the coefficient of fraction, that is important for the aerofoils. Okay, so on the aerofoils, we have the skin fraction coefficient. This skin fraction coefficient is exactly same thing, coefficient of skin fraction. So in the pipes, we have the fraction factor, that is depending on the Reynolds number and the roughness on the pipe wall. So that is the fraction factor, Darcy fraction factor, and skin fraction coefficient. So let's find out the both of these things and how they are related to each other. So only thing is that the CF formula is the watt shear divided by 1/2 density into velocity, velocity average square. And you will see these formulas in the book. So we have to find out how these formulas are derived actually. Okay. So again, I start with delta P is equal to 32 mu L U average upon D square. So what I'm trying to do is that I am putting my function in this form, in this way. So I'm putting the U average square. So I have to divide by U average so that I can make the one U average. Then I divided by the viscosity, density, and divided by the density. Then I multiply with the 2 and divided by the 2. And then I have written here the mu and L by D square. But actually we need the L by D here. So we have to take the 1D from here. So this will become the L by D. So I've taken the mu here and the 1D from here as a D here. I've taken the U average from the here and put it over here. And similarly, I put I got the one density here, the denominator, I put it over here. So this whole thing is the fraction factor. Okay. So then this is like L by D, and then this is the rho U average square upon 2. And this is the 1/2 rho U average square. So do you know what this thing is? Anybody? 1/2 rho U average square. What is this thing? The formula is the 1/2 rho.
Kinetic energy.
This what this term shows, what this term represents in this equation, means from fluid dynamics view, what this thing is, or what is significance of this term here over here. Okay, let me answer. This term is basically, you know about this term, 1/2 mv square. This 1/2 mv square is a kinetic energy, right? So I can write down this density as the m upon v, mass upon volume, into velocity square. U average is the velocity. So velocity square, so I can write down this one as a 1/2 mv square divided by, put it u as a, so u is the velocity and v is the volume. So divided by volume. So this thing is basically is the kinetic energy per unit volume. This term shows the kinetic energy per unit volume. Okay, it's clear? And the L by D actually is you can call this one as the aspect ratio of the pipe, and the mu upon rho into velocity into D. So you know that the Reynolds number formula is the density into velocity into diameter divided by the viscosity. This is just is the opposite of that formula. Mu is on the top side, viscosity, density in the denominator. So the velocity and diameter. So this is basically is a 1/RE. So that's why I put this one as a whole as a fraction factor, which is F. So this F is equal to 64/RE. Okay. So F into L by D into the rho U average square divided by 2. Okay, might be you are asking that how they come up with this formula. F is equal to 8 watt shear stress density into velocity average square. I will drive this thing also. Okay, now let's move to second formula. That coefficient of friction is given as a watt shear stress, which is basically is over here. And this skin friction coefficient, this CF is nothing. This CF is nothing but actually a drag due to friction. The drag coefficient due to the friction. So if you're familiar with the aerofoil, you know that there are two drags. One drag is because of the friction that is on the surface of the aerofoil, and second drag is because of pressure difference on the inlet on the downstream side. So this pressure, this skin friction drag is coming because of the CF value. Okay, so this is same thing actually you have studied in the aerofoils. Okay, so the CF is the wall shear divided by 1/2 rho U average square. And we know that the wall shear stress formula is a minus. We have to put the minus sign to make it positive quantity. And viscosity into the velocity gradient at the R is equal to capital R. So I can put the formula for the U, which is equal to this formula, du by dr. So we just derived this formula. You can see this formula. This formula, okay? So we put this formula over here. So I have to find out the derivative. So this becomes minus 4 upon R U average. So if I want to find out the wall shear stress, so I have to multiply with, one is that we have to multiply with the viscosity. And secondly, we have to multiply with the minus sign. This becomes plus 4 mu upon R U average, and viscosity also multiplied. So put this value over here, which is the 4 mu upon R and U average. And in the bottom, in the denominator, we have the 1/2 rho into U average square. So cancel out term and we get the value as 8 into mu upon rho U average square, U average into R. So if I make this R as a diameter, this will be equal to D by 2. And 2 will go into numerator, this will be 16. So CF is equal to 16 upon R, or RE. Okay, so then F equals 64 upon RE. So now you can write down this formula as a 4 into 16 upon RE. And you know 16 upon RE is equal to 16 upon RE. This is now from the previous slide. So you know 16 upon RE is equal to CF. So it means that the F is equal to 4 times the CF. So the Darcy friction factor is equal to 4 times the skin friction coefficient. Okay. So the only thing that is not shown on the slide, that is like you can ask a question that how they drive this formula. Okay, so let me show you. Okay, so you know this thing that this Darcy function. Please. Darcy friction factor actually is a friction factor. Friction, not fraction. Friction. It's a friction. Sorry for my pronunciation. It's a friction factor. Actually, this represents the losses in the pipe. So when the pipe flow is going in the one direction, so because of the wall effects, the roughness and the Reynolds number, this will introduce the losses. So pressure drop will be there. This is because of the losses coming from the friction effects. Okay. So this will, if you put this, this value will give you actually the value of the pressure drop along the pipe. So that much pressure drop you have to compensate by the pumping power. So you have to put the pump that can counter for the pressure drop that is occurring because of the friction effects in the pipe. Okay. Okay. So now we have the so this formula is now only is left, that is not derived here. So we know that the CF is equal to the wall shear stress divided by 1/2 rho V square, or the U average square. Okay. Clear? And what is the value of the F? This F over here. So you know that the 1 minute. See, the CF is equal to RE upon 16. And the F is equal to RE upon, sorry, it's written up in 1 minute. The CF is equal to 16 upon RE and F is equal to 64 upon RE. Okay. And the CF is also equal to the watt shear stress divided by 1 upon 2 rho U average square. So I can write down this one as a 2 watt shear stress divided by rho U average square. Okay. And also I know that this CF is equal to 1 upon 4 F, or F is equal to 4 times the CF. Okay. So I can write down this CF as a 1 upon 4 F. So from here I can write down the F is equal to 4 into 2 watt shear stress divided by rho into U average square. This becomes the 8 watt shear stress divided by density into average velocity square. So this formula is coming from this way. Okay. This formula is coming from in this way. Okay, so I think we have covered all the theoretical parts here, and tomorrow I will discuss this Moody's diagram, and then the analytical values for the different parameters that we will be comparing in our CFD. So tomorrow I hope that we are going to complete the CFD part as well. Okay. Any questions? Any questions? So now this is like end of the today's class.
No, Doc, but remember to give us the guide on installing the software. Thank you.
Okay, okay. And also I will be updating these lectures in the group, and slides also given in the group. Okay. Okay, thank you. Thank you. See you tomorrow. I'm going to share the classes, and I think that you will also get the link in the meeting. If you go through your account, you will see the meeting should be there, because I recorded on the cloud. So everybody should be getting the recording automatically in their own accounts. Okay. Thank you. See you tomorrow at the same time.